All right, we're going to start chapter 11. Chapter 11 is on momentum and impulse. Momentum was another concept created by Isaac Newton. And we write momentum in physics as lowercase p. And we define momentum as the mass of the object times its velocity. So the units for momentum is a kilogram meter per second. And momentum essentially is a property of the mass. So if it has no velocity, it has no momentum. If it has velocity, it has momentum equal to the mass times the velocity of the object. And so Newton said, well, look, you can do your three laws of motion in terms of momentum too, instead of in terms of forces. Because he said, look, in the first case, which is the inertia case, then your momentum is a constant. Meaning, if your velocity is zero, it's going to stay zero. If it's in the same direction, it's always going to stay in the direction. So the momentum would be a constant case. So this would be Newton's first law. What happens in Newton's second law? Well, in Newton's second law, he says, okay, what happens if the momentum is changing? So let's take the derivative of the momentum with respect to time. And if you do that, remember momentum is just mass times velocity, so this becomes the derivative of the mass times the velocity with respect to time. But the mass stays a constant, so this just becomes m dv dt when I pull the mass out front. But we already know that the derivative of the velocity with respect to time is just acceleration. So when we say a force, we set that equal to a force. A force is really just changing momentum with respect to time. And so you can look at forces, instead of being an acceleration on a mass, a force produces an acceleration, it's really producing a momentum change in the object. And then the third one is the equal and opposite is still the same. The equal and opposite force or the equal and opposite momentum change has to be on two separate objects. All right, so let's talk about impulse. Impulse is usually written as J. And impulse is usually treated for when you have things that happen over very short time frames. You're usually talking like milliseconds, something that happens very fast, like a baseball player hitting a baseball. The whole exchange happens in milliseconds, or a golfer hitting a golf ball, or something like that. You don't usually talk about it over long periods of time. But the momentum is just equal to the force times the time. Okay, as long as this is a constant force over a short time. Okay, or we can say in a more general form, if it's not a constant force, then we can actually integrate the force over the time, and then it works fine as long as force is a function of time. But then you have to know how force is a function of time, which most people don't. Now, if force is a constant, you pull the force out, you integrate dt, and you just get ft. So this is what we usually use for a constant force over a short period of time. But we can also relate force as be equal to the change in momentum. Impulse as the change in momentum. Well, remember what change in momentum is. That's just momentum final minus momentum initial. Or we can write this as mv final minus mv initial. Okay? So the the impulse, J, we usually use one of these two equations right here. Okay? And I always remember this equation up here. So that's how we have momentum and impulse and how they're related. If you know the force over the time, you could set this force over time equal to the change in momentum, because they're both equal to the impulse. That would have to be equal to that. And that would allow you to calculate like a final velocity if you knew a force and a time with the initial velocity. So let's think about it this way. If you're throwing a ball and the ball is going this way, so it has initial velocity in this direction. when the ball hits the wall, let's say it bounces back with the velocity final going this way. So that there's a change of momentum when the ball hits the wall. Okay? That change of the momentum is your impulse. Now, if V1 initial and V final are the same, is the change of momentum equal to 0? They are not, because you have to take into account the direction. So notice here, in this case, if we have positive going right, our change of momentum here is going to be, well, V final is negative, so this becomes M times negative V final, because it's going in a negative direction, minus, from here, MV initial, but this is in a positive direction. Now V initial and V final are the same, so it bounced off the wall with exactly the same momentum. This is going to be equal to negative MV initial minus MV initial, or negative 2MV initial. So the change in momentum, which is equal to the impulse, is equal to twice the momentum. So when it bounces off of the wall, when the ball bounces off the wall, it has a larger impulse than if it just sticks to the wall. Because if it just sticks to the wall, then when the ball comes and hits the wall, the final velocity is just equal to 0. And then our change in momentum is going to be equal to momentum final minus momentum initial. But momentum final is equal to 0, so the change in momentum is just equal to negative MV initial, which is equal to impulse. It's only half the impulse than when it bounces. So there's a much bigger force, because remember, change in momentum is equal to force over time, that the wall feels when it bounces off it than when it just hits it and sticks. Think of it this way: when it comes in, it absorbs this momentum, the wall does. But if it bounces back, not only does it absorb the momentum, it has to give it momentum going back, and that's why it's double the momentum. All right. Now, for most of the stuff we're going to use it for, and this is typical physics here, you use the conservation of momentum, and you must use the conservation of momentum whenever you have a collision. Because in most collisions, the energy isn't conserved. It can be in certain cases, but most of the time energy is not conserved, but momentum is. Which really says that the momentum initial is equal to the momentum final. So this is the second of our conservation laws. Remember, we already had a conservation energy. This is conservation of momentum. Or what we usually say is the momentum of particle 1 with its initial velocity plus particle 2 with its initial velocity has to equal to particle 1 with its final velocity, particle 1 final, plus particle 2 V2 final. Notice you have to be really careful. We have lots of subscripts here. Okay? And the problem is here there are 6 different variables. There's 4 different velocities and 2 different masses. So this becomes very hard to solve, and that can be a challenge. And if we have a whole lot of particles, we can even add up momentums. So you can think of it as a group of particles is the momentum of all the particles added together makes the momentum of the conglomerate, or the whole group of the particles. All right. Now there's specific cases when we have collisions. And when we have these collisions, we can make things simpler. So we have what we call an inelastic collision. And then an inelastic collision, 2 particles or 2 objects collide and stick together. In this case, it makes a whole lot simpler to do. We're going to use the equation right here, this equation, but we're going to simplify it. We're going to assume that V2 initial is equal to 0. Or, if it's not equal to 0, we can always pick the reference frame where it is equal to 0. Remember, we talked about the fact that all velocity is relative. Well, if this was moving, well, you just pick that everything moving with respect to that has a velocity, but it is moving with zero velocity. So you just set your reference frame to it, and you can set it equal to zero. Well, that's the case, and this term will go away, and we got m1, v1 initial. But over here, we have the same final velocity because they stick together. So you're just going to get v final times m1 plus m2. Or for an inelastic collision, remember this goes with inelastic, this problem, or this equation that had 6 variables, is now being reduced to the point where there's actually only 3 variables. Actually 4 variables, 1, 2, and then 2 masses. So it simplified it significantly. But remember, this can only be used if 2 objects collide and stick together and the initial velocity of the second one is equal to 0. Okay? All right, then we also have the case of an elastic collision. In an elastic collision, both momentum and kinetic energy are conserved. So both the momentum of the 2 particles and their kinetic energies have to be, the total of those have to be the same initially and finally. This makes for an interesting situation. We don't really see this usually in large macroscopic collisions because the energy is usually rarely conserved. But this does happen with like subatomic particles, and so that really makes it easier to make